You know, every time you fire up a video game or check your phone's GPS, you're tapping into this incredible hidden mathematical language. And that language is three-dimensional geometry. Now, I know it might sound super complex, but it's really the invisible blueprint for the entire world we live in. So today, we're going to pull back the curtain and see exactly how it all works. All right, so that leads us to the big question. We all live in a 3D world, right? We get height, we get width, we get depth. It's intuitive. But how do we actually turn that gut feeling into a precise mathematical language? Well, that's the puzzle we're going to solve today by breaking it down one building block at a time. Okay, so to really appreciate the jump into 3D space, we've got to start somewhere simpler. We have to go back and understand the limits of a 2D world first. So our journey is going to begin in a place you probably remember from math class, that perfectly flat world, sometimes called flatland. Think back to drawing graphs on paper, right? Every single circle, every line, every parabola, they were all just stuck there, trapped on that flat surface. They were defined by only two directions. You had the x-axis for going left and right, and the y-axis for going up and down. That's it. But what if we want to break free from that page? This is the revolutionary leap. We introduce a third direction, a brand new axis that literally gives our shapes flight. And that's the z-axis. It represents depth, the freedom to move forward and backward. I mean, just think about that difference for a second. In that old 2D world, a shape is just stuck. It's drawn on the ground. But now, with the z-axis, that same shape can suddenly lift right off the page and just float anywhere it wants in open space. This one simple addition completely transforms our entire mathematical universe. All right, so now we have this vast new 3D space. That's great. But how do we find our way around in it? Well, it's kind of like how every house needs an address. In this universe, every single point needs its own set of precise coordinates. And that address, it's just a simple set of three coordinates, x, y, and z. It tells you exactly how far you need to move along the x-axis, then how far to go along the y, and now, critically, how far up or down to go along the z. You put those three instructions together and boom, you can pinpoint any location in space, anywhere. Okay, but what about finding the distance between two of those points? Turns out, it's actually just a 3D version of the good old Pythagorean theorem. You just take the square distance for x, you add the square distance for y, and now you just tack on one more term, the square distance for z. It's such a beautiful, elegant upgrade, isn't it? So, knowing where points are, that's half the battle for sure. But what about direction, right? If you're going to travel from one point to another, which way are you heading? To answer that, we need something more than just coordinates. We need a vector. So what is a vector? Well, you can think of it as basically an arrow in space. It has both a length, times, and a direction. And to define that direction precisely, what we do is we measure the angles it makes with each of the three positive axes. We call them alpha, beta, and gamma. Now, if you change the vector's direction even a tiny bit, those three angles will change. They are its unique directional fingerprint. Now, to make all this information useful for math, we do something specific. We take the cosine of each of those angles, and this gives us three numbers, which we usually call L, M, and N. These are the direction cosines, and a good way to think about them is as the official, standardized coordinates just for a vector's direction. But here's where it gets really cool. This is the aha moment. What happens if you take these three direction cosines, L, M, and N, and you square each one, and then you add them all together? Well, no matter which way that vector is pointing, no matter what, the answer is always, elegantly, 1. This simple rule, L squared plus M squared plus N squared equals 1, that is a fundamental truth of 3D space. Okay, a quick but super important distinction here. For any given direction in space, there is only one unique set of direction cosines. It's like a fingerprint. There's only one. But there's an infinite number of things called direction ratios, which are just any set of numbers that are proportional to the real deal. So just remember, the direction cosines, they're the one true standardized measure. All right, so we've located points, we've defined direction. Now let's take that knowledge and use it to build something much bigger, an infinite, perfectly flat surface that's just floating out there in space. And that, of course, is what we call a plane. So to really get a grip on what a plane is, you have to know about its normal vector. Just picture a tabletop. The normal vector is like an arrow pointing straight up from it, perfectly perpendicular to the surface. And that one single vector, it defines the exact tilt and orientation of the entire infinite plane. It's incredibly powerful. So how do you actually lock a plane into position mathematically? How do you define it? It's surprisingly simple. You only need two things. First, pick any single point that the plane has to pass through. And second, define the direction of its normal vector. That's it. With just those two little pieces of information, you've defined one unique, infinite plane in the entire universe. And this all connects right back to the standard equation for a plane. You've probably seen it. ax plus by plus cz plus d equals 0. Well, those first three numbers, the a, b, and c, they aren't random at all. They are literally the direction ratios of the plane's normal vector. So the tilt of the plane, it's been hiding in plain sight this whole time, right inside its own equation. So let's recap. We've gone from points to vectors to planes. We've been building the essential language of 3D space. But let's be real. Why does any of this matter? Well, because this abstract math, it's not just theory. It's the invisible engine that's driving our modern world. I mean, just think about it. Every single character in a CGI movie, every car in a video game, at its core, it's just a crazy complex collection of points, vectors, and planes being calculated millions of times a second. Your phone's GPS? It's constantly figuring out your X, Y, Z coordinates on the globe. This stuff isn't just math on a page anymore. It's basically the source code for our modern reality. And when you boil it all down, it all started by just adding one simple line, the z-axis. That single addition took our math from a flat drawing on a piece of paper and transformed it into a model of the entire universe. Which, leaves us with a final, kind of mind-bending question. If that's what adding a third dimension can do, what new reality is waiting for us in the fourth?